Welcome everybody. So today we're going to try to answer the question, how far has an object moved when all I know about it is the velocity as a function of time? And we're going to go ahead and use our definition for velocity and try to intermediate between these two representations. The very first thing that I'm going to do is I want to know how far has the object moved. So from this definition, I need to get the position alone. And the only way to do that is to do something that your math teacher might have told you not to do, but is perfectly all right, which is multiply both sides by dt. And I'm going to rewrite this expression then as dx equals vx dt. And now I'm going to try to interpret this new equation and especially think about how it works with the graph. So the very first thing I want to look at here is the dt. Now, as you might be able to guess, from the little d, this is a small infinitesimal interval of time. So if I wanted to draw this on my graph, it would be some little interval of time like that. And I could pick any interval on the graph that I want. So I could instead pick this one or this one, and those would all be perfectly reasonable dt's to choose. And in fact, what I have just done here is I have taken the time axis and I've chopped it up into little pieces. So I'm going to go ahead and label that on my equation. What I've really done here is chopped up the time. Then the equation is instructing me to multiply the velocity times that small dt. So again, I'm going to go over here to the graph, and I'm going to say, where is vx? Well, that's the thing I'm representing vertically, so it should be the height of the graph at each of these points. And I could label each of those vx. And again, what I'm really doing here is I'm multiplying these together. So what I'm really trying to create is a little rectangle that is the product of vx and dt. And all of these little rectangles, any particular one I could label dx. And as a result, I'm going to say that what I've done here is multiplied to get dx. The last thing that I want to do in thinking about my question is figure out how far I've traveled. So I don't just want to know a small change in the position. I want to know a big change in the position. And the only way to get that from a system like this is to draw a whole bunch of additional rectangles and then add all of those rectangles up. So like dx1 plus dx2 plus dx3, all the way across the board. And if I start over here and I go all the way to the end, that would tell me the total distance traveled. To do that in my equation, what I'm going to use is an integral. So I'm going to go ahead and write my integral here. This is an integral on both sides of the equation. And we'll do many integrals in physics, and almost all of them will be definite integrals. So we need limits of integration here. I'm going to choose really generic limits for today. I'm going to go from some initial time to some final time. And those could be any times I want on here. So I'll go ahead and label that. Here I'm integrating with respect to time. And here I'm really integrating with respect to x. So I want the positions that correspond to those times. Now I can do these integrals. This one is pretty easy because it's just the integral of dx. So I'm going to get x final minus x initial. Over here, I would need more information about vx to be able to evaluate this symbolically. So there's not much I can do here except rewrite the integral from ti to tf. And the very last thing that I might be interested in doing, right here, by the way, right, this thing is my delta x. So I've found an answer to the question, how far have I traveled? But sometimes I'm more interested in a question like, where am I? What is the final position of my object? So I could solve that equation for x final, and I would simply get something like this. So now I figured out how to get both how far and where my object is, and I thought both with the equation and with the graph.